Imagine we have a Carnot engine with a system just like this inside box that this system has contact with two reservoirs, let's say the blue here as cold and the red here as hot. By second law original statement, not all heat can be converted to W even in ideal. So then if we add output here, let's say for W or work, we need to define the Carnot engine efficiency eta as ideal reversible heat engine. By Carnot theorem, we have that eta is equals to this, which the original definition is about delta W divided by delta Q at hot reservoir. Here, we assume that delta U not far from zero, or here, this system at least is quasi-static or for very least nearby equilibriums. So by the first law of thermodynamics, this W we can expand as this. After some modification and simplification, we will get the final equality is about this. And here, you may familiar that this definition proportional to entropy we defined in previous video. And if we modify again, delta Q code is in minus sign because it made heat out. But now there's a question: what if there are Ti many more reservoir? Well, it's not necessary Carnot engine that may be another heat engine, but this is too complicated. Why? We only know about Carnot engine that connected two reservoir, but now with many reservoir. Here's the trick. At each reservoir, we can connect each reservoir to one reference reservoir that each reservoir not interact each other but only interact with this reference reservoir. So each reservoir will interact to reference reservoir as little Carnot engines. So that's why we can define the equality before with the summation here for each I reservoir in discrete, and for continuous limit we will have this counter integration. And zero here, we assume that the system of heat engine there is reversible because there's no heat flow to the reference reservoir. So the remaining heat engine is this collection of Carnot engines. How about if the system is irreversible? Here, by some technique just I said, we can change this zero by epsilon. That epsilon here is the ratio that just like before but now for reference reservoir. Here, we multiply the both sides by T0, the reference reservoir temperature, and assume that both epsilon and T0 greater than 0. So to compensate this equality, we need to give work to make these Carnot engines become Carnot engines. So that means this term is about heat and this term is about work to compensate the Carnot engines. And by second law, the work term here need to be positive because we need to add work to compensate the system. And the next consideration is about efficiency. Here, in this point of view, the overall system is about one reservoir T0 convert all its heat to work. This thing is contradiction to the second law. And that's why at the end, in continuous cycle point of view as infinitely many and continuous Carnot engine, we have this inequality as Clausius theorem, so that's why we can define difference of entropy equals to this.